Hi, this is Dr. Della Corte again with Physics 313R. Today we're going to talk about quantum algorithms in our Introduction to Quantum Computing course. So, as a reminder, we're basing these lectures off the book Quantum Computing for Everyone by Chris Bernard. I highly recommend buying the book. Um, Measurements. We already learned that whenever we are measuring a qubit, we either get a state up or state down or north or south or one or zero as a result. So if we are repeating the same measurement, we're going to get the same result. But if we rotate the measurement, then we lose our certainty of the outcome, and then we can get two different outcomes. And if we select, let's say here again, the south pointing one and send it through the same magnet that we had at the beginning of the experiment, we again lost all of our information. So that's a very interesting effect of quantum mechanics that we discussed already at length. We learned already that quantum calculations require some linear algebra. Today, we're going to use a bit more of this. So we need to be able to calculate the so-called matrix product here, where we build a transposed matrix of the column vectors of a set or collection of vectors. And if we transpose it to turn the cats into brass and multiply it by the cat matrix, and we find that that product gives us an identity matrix of dimension n, given that there are n basis vectors, then we know we have an orthonormal basis. Given that we have an orthonormal basis, we can now take any vector in n and represent it as a linear combination of these vectors. We do that by solving the system A transposed multiplied by that vector we want to express. And the coefficients that we find here are what we call the probability amplitudes. And so once we have these probability amplitudes, C1, C2, and so on, we can use those to calculate the length of the vector by using effectively Pythagorean theorem in higher dimensions. Okay, great. So you should be able to do this by now. We also learned that spins can be used to represent qubits. So if we have electrons and have a spin, they can be used to represent a qubit, or we can also use the polarization of photons to describe them. We saw some interesting things, for example, that you can establish safe communication channels, for example, for the BB84 protocol. Great. We then looked into the problem of entanglement, where we take two qubits and we somehow entangle them with each other, and then we give them two people. So I call those Alice and Bob. And we said when we have these two entangled qubits, they are no longer separate entities, but they share a global property with each other. And so instead of looking at them as two-dimensional vectors, we have to look at the tensor product, a four-dimensional state. And we saw that if those two qubits are entangled and Alice and Bob are at large distances from each other, then if one of them does a measurement on the qubit, that impacts what the results of a measurement on the other qubit would yield. And this could be considered a spooky interaction at the distance. However, we just say that that is a global property and that the entangled qubits are no longer individually, separately a thing, but they're now this combined thing where the connection transcends space, which is crazy, but it works and seems to do very well in experiments. Okay, we also learned about quantum clocks. And one thing that we saw, for example, is that if you have two quantum clocks that are in an entangled state like this, if the first one has a result like 12 p.m., then the second one will definitely be at 12 p.m. So it was sort of a visualization of what entanglement meant. Wonderful. We then learned about classical gates, and we said that there's a specific type of gate, it's so-called reversible gate, that allows us to deduce what the inputs are given the outputs of a gate. And for that to work, we had to have the same number of input arguments as output arguments. And while some functions like the normal NOT gate would not provide that, we have, for example, the controlled NOT gate, where we have an additional input and additional output variable that allow us to create that allow us to create that reverse connection between outputs and inputs. Then we saw that there are some gates that have a nice property, which is called being functionally complete. So the Toffoli gate and the Fredkin gate, they are wonderful because you can build any classical circuit out of a combination of these gates, which was quite nice because we saw you can simulate pretty much anything with simply billiard balls. Go back to that lecture if you want to learn more about it. Okay, great. Then, having this basic understanding, we were able to look into some of these hyped words like superdense coding and quantum teleportation. And we saw that if Alice and Bob share entangled qubits, they can use those to, on the one side, communicate more efficiently. So they are able to share 2 bits of information using just 1 qubit. That is the idea of superdense coding. And the basic behind it was that they're using a smart combination of encoding gates and decoding circuits, where we learned about the 3 basic Pauli gates that are used by Alice to encode the 2 bits. And then Bob receives a qubit that he can then use to run through a reverse Bell circuit, which allowed him to say clearly which combination of 2 bits were sent to him. Quantum teleportation has the idea that someone has a bit in their possession, a qubit in their possession, which has a certain state. And because that person also shares an entangled qubit with someone else, that qubit with that state information can be that state information can be transferred through the entanglement onto the qubit that the other person has. And we saw that that can be done if Alice encodes her special qubit in a special state with the entangled qubit using a reverse Bell circuit, and then if Bob uses the right Pauli gates, where Alice has to send him 2 bits that help him identify which one it is, and uses the right Pauli gates, then he's able to make sure that his qubit is in the same superposition as the one that Alice wanted to send to him. And those fields have evolved quite a bit since the book was written in 2019. There was actually a Nobel Prize in 2022 that was given to for the Bell inequality test that is sort of based on the same techniques here using the Bell circuits. So the field is evolving, and there are still papers published every year on or every month, I would say, on different progress with regards to superdense coding and quantum teleportation. So it's very likely that you're going to see something like that on Google Scholar or so, and hopefully you will be able to now, in your mind, place it in the right context. Okay, great. But today it's all about quantum algorithms. So here is a little story that I found on the internet that I thought is a nice metaphor for what a quantum algorithm is. So imagine that your mom asks you to write Valentine's cards to every classmate on Valentine's. This seems to be a very boring task. So you might want to use a computer. So in a classical computing sense, you would tell your computer, hey, write me a card for each of my classmates, and then you print them out and you get these cards, and then you have to give everyone a card. So that's the classical way of thinking about it. If you think about it from a quantum perspective, you would say, well, instead of writing one card after the other, I'm just going to write all cards at once. And once I've written all of these cards, I distribute these cards. But if you do it that way, you can't be sure that the right person gets the right card. And so the idea of a quantum algorithm is to change the odds so that by using this algorithm, you can make sure that the one card that matters most is delivered to the one person, the girl that you like the most, or just the thing that you care most about. So what we have seen before is in quantum computing, we are able to mess around with the probability amplitudes and use the phase information in it to change the likelihood that a certain outcome is being reached. And so the 2 ideas that we are combining are first superposition of states. So instead of writing all cards one after the other, we write all cards at once, so all possibilities are there. And then we make sure that only the state that we care about is measured at the end, or that event that you truly care about has a remaining probability of occurring. And so this combination of superposition of states and only measuring what really matters will be the basic idea of all quantum algorithms that we're going to cover. Of course, we have to ask ourselves first the question, why do we even care about different ways of algorithms? Is there anything better about a quantum algorithm than about a classical algorithm? And in order to understand that, we have to think for a moment about how we actually assess the speed of an algorithm. And so there's a whole field around that can do complexity analysis. We're just going to touch on it shortly. And we use the example from the book where the question is, if I give you a number like 35 and ask you to find two prime numbers that multiplied with each other make up 35, how long would it take you to do that? So 35, yeah, you know your multiplication table, so you know maybe there's a 7 in there and there's a 5 in there somewhere. But it takes you a moment to think it through. On the other hand, if I ask you to multiply 7 and 5, you'll be pretty quick at responding, oh, the answer is 35. So we see here a problem that's slightly more difficult on one way than on the other way to solve. This can get dramatically more difficult if we increase the number of digits in a number from 2 to, let's say, 5. And if I ask you to find two whole numbers that form this product here, 88,631, it will take you a long time to do that. On the other hand, if I ask you to multiply 337 by 263, you can probably sort that out in a couple of minutes if you remember how to do your long multiplications right. So this is an example of a problem that gets dramatically more difficult to find a solution, but it stays reasonably simple to check the solution. So when we have a problem like that, and we say it's kind of like an exponential, very difficult problem to solve, however, the answer can be checked in a reasonable amount of time, then we call this a NP problem. So it's a very complex, hard problem, but if we have the answer, we can check it reasonably fast. Okay, so any task that can be achieved in a reasonable amount of time, we say it takes a certain polynomial time. And because it's polynomial time, we saw it belongs to class P. Okay, so if we, there's some formalism, we don't actually need it that much, so we can kind of skip through it here a bit. And just say that there are these measures that say if you have a problem and the amount of time t it takes to solve it, given its complexity n, so for example, the number of digits here, if that time is smaller than some polynomial, so n to the power p, where p, even if it's 20, n to the power 20, very hard problem, takes a lot of time, but it's still bound by a polynomial number that will be tractable. It means that even though the problem might not be solvable today, if we use Moore's law and know that computers get faster every, 18 months or so, then eventually it will become solvable because we are going to have more compute at our disposal. On the other hand, if the time is greater than some value c to the power n, so where it grows exponentially with the number of digits in our example, then we say, oh, this is an exponential time that's really hard, that's intractable. And even if for small n's this problem is solvable today, making n a little bit bigger, it won't be solvable tomorrow. So we really like to stay away from those problems there. They're very hard for classical computers. Okay, there is a bit of an excursion in the book on the question, are NP problems all P problems? And no one has solved this yet. If you want to solve it, you can win, I don't know how many millions of dollars the Millennium Prizes are right now, but you can grab quite a bit of money if you can prove that this is true or not. So maybe you want to just write a paragraph or two in your study journal so you're aware of this problem, which has nothing to do with this class, but hey, what we see from this here is there are some problems that are really, really hard. We think they are living in this space that is not solvable directly, but we could check the answers. So there are some problems that are in NP. If we assume that, we don't know that's true, but we assume that there's some problems that live in NP. They're very, very hard, exponentially hard to solve. but the answer could be checked. And then there are some problems that are just polynomial problems and they're solvable. If that's the case, then there is a different class of problems that would be solvable in polynomial time, but only if we use a quantum computer to solve them. So those are problems we call in the class EQP. So in the class EQP, those are all quantum algorithms that problem solver with a quantum computer. Some of these problems are going to intersect with the class of NP. And so everything in this intersection are potentially problems that could benefit from a quantum computer. So how can we show that this intersection even exists if we don't know that P is different from NP? Well, one thing we can do is we just invent a different way of measuring complexity. And then we use that different measure to prove it's possible. Or second, we construct a really, really cool algorithm that solves a very, very hard problem. And if we solve that hard problem in polynomial time, and we see that Shor's algorithm does something like that in the next lecture, then, we're there. Great. So what is this other measure that we could introduce? So one measure that we could introduce is called query complexity. Query complexity simply counts how often you call a specific function. So let's say the function is something that the quantum computer can do. It's a black box. We don't know what it is or what it can do or what it can't do. We just know it's there. And then we can say we can throw a certain input into the function. It crunches and gives us an output. If we have a certain problem that can be answered by throwing smart inputs and outputs into this function, then we can count how many different inputs does this function take before we have enough outputs created that allows us to answer our question. And we say every time we call this function, it costs us a unit of 1. So we can compare different algorithms with each other simply by seeing how often do I need to call this function, this black box. You can already see that that's a problem, right? If this black box function would require you to fly to the Mars, pick up a rock, bring it back to Earth, and do a measurement on it, that would cost a lot of time and effort and resources, and it's not quite feasible to say it's faster than a classical algorithm. So I don't know what's a good example. But if you have a very cheap function, it might be way cheaper to call that function 1,000,000 times rather than calling an expensive function only once. And so we are completely smoothing over that problem, especially knowing that quantum algorithms might be very, very expensive every time you call a function, especially compared to the performance on classical computers. We ignore that, which we might discuss next lecture a bit what the limitations of that are. But for now, we just do it because that helps us progress in our discussion. So for now, we just remember every time I call a quantum function, it costs me 1 unit. Every time I call a classical function, it costs me 1 unit. The question is, how often do I have to need to call either function before I get the final answer? If I get the final answer with less calls in the quantum case, then the quantum algorithm will be superior to the classical algorithm. The first person to show that such an algorithm exists was David Deutsch in 1985 when he published the Deutsch algorithm. He, by the way, won a nice prize. Oh, maybe I'm blocking his face here. You can see he looks pretty happy with himself here. He won $3 million a couple of years ago. So-called breakthrough prize from the Zuckerberg group. Okay, cool. So the Deutsch algorithm. The question here is, we have a function f that's a black box. We don't know what exactly the function is, but we know that this function can be one of 4 different types of functions. And the 4 types of functions do the following. The first one, called f0, takes in the inputs 0 or 1, and it produces a 0 or 0 output. It's a very boring function. It takes things that come in and always spits you out a 0. The second function is f1. That one takes the input 0 and 1 and spits out 0 and 1. It's also a very boring function. It takes a 0 and gives you a 0. It takes in a 1 and gives you a 1. It's an identity operation. It doesn't do anything. Finally, there's an F3. F3 takes in 0 and 1, and it in every case spits out a 1. So it looks like a broken function. It doesn't care what you throw in, it always gives you a 1 back out. Similar to how F0 just gives you zeros, F3 gives you just ones. And then there's a function F2. F2 is going to give you for a 0 or 1, a 1 or 0. That's a bit more interesting because it flips the bits around. So at least it does something. Everything else didn't do anything really. Okay. But what we notice is the functions F0 and F3 on the left, they produce constant outputs, either just zeros or either ones. The functions on the right, they produce a 0 and a 1 as an output. It's always a 0 or 1. So those are called balanced functions. And now the Deutsch algorithm is the answer to the question of how many calls does it take before I can figure out if a black box function is either constant or balanced. Okay, we don't care if it's F0 or F2. We just care, does it belong to the group of constant functions or to the group of balanced functions? Okay, so how often do we need to query this box to find it out? We can look at it from the two different perspectives. First, maybe with the quantum way. Let's see if I find a space for my picture here. So let's ask a quantum question. So here we have a function f. We don't know what it is, but it is a magical function. And that function can produce as an output. So input are the two numbers 0 and 1 that go in, and as an output, it spits out the state x, and then it produces here. Remember this little circle with the cross in it? That is the C naught, or the controlled not operator. That's the same as adding the two numbers and then modulo 2ing them. Okay, so that's what this function does. So if we plug in a 0 and a 0, it spits out a 0 for the x state, and then if you have a 0 here, then you have f1 of 0, so you just get the f10 state out. Or if you plug a 0, 1 in, it's going to give you a 0 or the f1 c-naughted with the 1. I'm not sure why they switched this around in the book. I would have written 1 c-naught with this guy, but anyway, you can, if you do it with the c-naught operator, commutes, so you're fine doing this. Okay, great. So these are the 4 possible outputs. And now the question is, how often do we need to ask this gate before we know if it is balanced or constant? It turns out that if you use just the basis vectors, so just zeros or ones, you have to run all, you have to do at least 2 calls. So run 0, 0 through it, 0, 1, and then you know if you're going to get always constant or always balanced output. But the trick will be now to use a superposition. And if we do that, we will only need 1 call. Now the math is not completely trivial to this, so I hope I can walk you through it. The way we're going to set it up is we're going to use this function f here as shown down here. So instead of f1, we're writing here f1, split it up a bit, and say instead of just putting in x's and y's, we put in 0 and 1, but 0 and 1 will be put into superposition first. We learned last time that if you use a Hadamard gate, then you can put the 0 in half of the time first basis vector, half of the time second basis vector, and the same thing with the 1. There's just the minus sign that comes in. Okay, so we're going to put 0 and 1 into superpositions, run them through the function, and then we take the outcoming qubit on the top, run it again through a Hadamard matrix. We learned before those are reversible, and then we can measure the outcome, and maybe that will help. So let's see how this works. So if I take a 0 and 1 as an input and run them both through the Hadamard gates, the Hadamard gate is going to take the 0 and put it in superposition 0 plus 1, and it takes the 1 and puts it in superposition 0 minus 1. And now if I want to get rid of the circle with the x, the tensor product, I have to multiply each of these terms, or tensor product each of these terms with each other, and we learned a shorthand for that. The 0 tensor product 0 just becomes state 0, 0, and then we have the 0, 1, 1, 0, and the 1, 1 states. Okay, and then these states are going to go through the F gate. And now what happens here, we got to look at the, so let's look here what happens real quick. The 0, 0 state, this is up here, this guy, that is going to be put into 0 tensor product F10. Did I mark this up? No, I didn't. So let's use my pen. Pen. Go away. So we want to replace this term here. Come on. This term. So we see it's defined up here. When we have 0, 0, then after F, we have this guy, and that is what's being written out here. Okay? And then the 0, 1. Yeah, and then we have minus 0, 1. 0, 1 is this guy here. That gives us this term, and we write it out here. Okay, so this way you can work yourself from this equation to that equation. So far, we haven't done anything super smart yet. That starts on the next slide. Here we're having the gory details of the Deutsche algorithm, where we're taking this expression and manipulate it a bit. The first thing that we note is if I have a function, it's any of the functions f, fi of 0, and I subtract from it fi of 0 with the C naught operator 1, then this turns either into 0 minus 1 or 1 minus 0, depending on what f1 is, fi1 is. So if I have, if this guy, come here, if this guy here turns, for example, into a 0, then this guy is a 0, and 0 C naught 1 is just going to be 1. And so if this is 0, then I get 0 state minus 1 state. And on the other hand, if this function is equal to 1, then I get here 1 plus 1, and 1 plus 1 gives me a 0. And then I get the 1 state minus the 0 state. Okay, so we can check both of these assumptions. So we can simplify this term. In order to make that even better, we smartly rewrite this. So we say that this expression here is going to be equal to 0 minus 1 multiplied by this minus 1 exponentiated. Why do we do that? Because if this is 0, anything raised to the power 0 is 1, then I don't get a plus sign here. If I then I get a plus sign here. If it is 1, then minus 1 to the power 1 is just minus 1. That gets me a minus sign, and that flips the signs inside of these parentheses around. And so this way I can recover the two expressions that I had before. Okay? And so we can do that either for the state plugging in a state 0 or plugging in a state 1 into the function. Doing that allows us now to go ahead and rewrite the expression we had on top. So where we had before, for example, this guy, we are now able to use this equation here to rewrite it like that. And then we can do the same thing for this expression, rewriting it like that. Okay, once we have done that, we see now a bunch of parentheses and tensor products. It looks very messy, but we can massage it a little bit, maybe clean it up a little bit. And we are just flipping around here where these terms are. So we're taking the minus 1 terms and pull them out Those are just scalars inside of the tensor product, so you can apply them on either side. So we move them all out. You see that here. So these guys here, this one and this one, have been moved in front of the 1 and 0 respectively. And now we've written it like that, we might see, oh, there's actually some symmetry here. We might realize that there is something that looks like ax plus bx. Maybe if we take the green pen here, we see that this guy here is the same as that guy. And so those are just like x's that have a different thing, a or b, in front of them. And so we can actually just go ahead and factor that out. And if we do it, we get this expression here on the right. So the 0, -1 states have been factored out. And now it starts to look a little bit easier. Oh, here, this is the term we just pulled out. One more thing we can do is we can split this 1/2 into 1 over square root of 2 in front of both of the states. And what you see now is, hey, here on the left, I actually just have a superposition of the 0 and 1 states with some probability amplitudes. And on the right side, we have again a superposition of 0 and 1, where they're in the same state, same probability between both states. And now these two qubits that we got here, because there's a tensor product between them, the left corresponds to a two-dimensional vector, the right to a two-dimensional vector. The left one is the qubit that comes out on top of the function. And both of these qubits are not entangled with each other. Okay? So if we now look at what comes out of the function f, on the top here, we have these top qubits coming out. And now depending on which function f we had, they will take a different value. If the function f was the 0 case, where no matter what you plug into the function f, you always get a 0 returned, then you have a -1 to the power 0, just a 1, and -1 to the power 1 is to f1 to the of 1, which is again 0, -1 to the power 0 is again 1. You get the state square root of 2, 0 plus 1. Right? So that is what you would receive out of the function f1 if the black box were function f0. Similarly, and then if you run this function through the Hadamard gate, the Hadamard gate is the reverse of what it did before, right? When you had a 0 that came in, you get this state to come out. If you throw this state through the Hadamard gate again, then you get the state 0 out. And so if you measure, you get with 100% probability the state 0. If you repeat this exercise for the different functions f1, f2, f3, you'll find these other 3 output cases. And if you run each of those through the Hadamard gate, you will see that f1 and f2 will either be plus or -1 state, and f3 will be -0 state. And so if you measure, you can see that for f0 and f3, you're always going to get out the state 0, because they have the same probability. You have to square the amplitudes. And f1, f2 will always give you the state 1. This means after running this circuit here, if you measure 0, you know you had function 0 or 3, and those are the two constant functions. So if you do that, then you know for sure you have constant. If you measure a 1, you know for sure it's balanced. And so this shows that with just a single query of the function f1, we are able to find out if the function that we looked at was either in the class of balanced or constant functions. But now going back to this function, were really boring functions, right? You either get zeros out or ones out, or one of them did nothing and the other one flipped the bits around. It is not a useful thing. However, it was the first time that someone showed that you can reduce this query complexity by using a quantum computer instead of a classical computer. So this is a very, very nice foundational experiment or foundational theory for an algorithm here. but it is still far removed from being useful in any way. It's very much constructed. Interestingly, if you think about timelines, after this in 85 was published, it took quite a bit longer before Deutsch, in collaboration with this Josza guy, was able to generalize this. And this is again not a really big step forward, as in now we can do something useful. It is just showing that instead of figuring out if a function f with one input is balanced or constant, you can use a function f with n inputs to show if it's balanced or constant. Maybe you can think about it for a moment by yourself and write in your study journal, how many calls would it classically take to figure out if a function of n arguments is balanced or unbalanced? Does it always repeat one? Does it always repeat zero? Or does it have an equal number of zeros and ones being produced? In the classical case, if you work it through, you will find it is 2 to the power n minus 1 plus 1. So you have to look through half of the bits before you can be sure that it is either balanced or unbalanced. So in a moment where you find it's 0 or 1, then if you have both responses, you know it has to be balanced. But running half of the inputs through and I always get a 0, it could still be balanced. You just got unlucky. But if you then take one more than half of them, then you're going to get either another 0 and then you know it's all constant, or you get a 1 and you know you're balanced. So worst case scenario, if you randomly bootstrap from it, you would do a lot better than this, but worst case scenario, classical. The quantum algorithm, however, on the other side can get this again all done within one call. In order to do this one call correct, we use pretty much the same setup as before. We're going to run all of the qubits through, so we have all of the states up here for n. For n arguments, we have n zeros, and they're going to run through a Hadamard gate. And down here, we have the state 1 that just runs through a Hadamard gate, and then f does whatever f does. Okay, so the difference here is that you have n zero states. So you have a very, very high dimensional vector. And if you have a high dimensional vector, you have to have a huge matrix to multiply it with. So the Hadamard gate is now a way more complex entity. And I decided to not go into great depth of how that what that matrix looks like. You can look at that in the book. I think the main idea from it we can take away without doing that detailed linear algebra here. So if you run that state for that Hadamard to the power n, if you want to think about it like that, then it's doing something very similar to what we have seen in the one-dimensional case. It is going to produce at the end probability amplitudes for the different states. And the probability amplitude after running through f and then running again through the Hadamard gate will look something like this. You have 1 over 2 to the power n, where n is the number of inputs, and then you have either a minus 1 raised to the power of f with the inputs, plus minus 1 to the power of f with all of the inputs, and the last bit is now turned from 0 to 1, all the way through where all of your input bits are ones. And now, if you think about this, this is going to be the sum over all of the minus ones exponentiated with what the f function produces. If the f function always produces zeros, then you are just going to add up ones. If the f function always produces minus ones, then you're just going to add up minus ones, and then you normalize it by the number of qubits effectively. And so you are going to get either a plus 1 or a 1 for a constant function. And if you have a balanced function, then half of these minus 1s here will be plus 1, and the other one will be minus 1. So they cancel out, and you're going to end up with a 0. So if you just measure the 0th qubit, and if f is so if you measure the output up here, so for whatever superposition these states are in, and you find out that all of the measured qubits are 0, then you're dealt with a constant function. If at least one of them is going to be a 1, then you will have dealt with a balanced function. Okay, so that's the generalization of the Deutsch-Josza algorithm. Then there's a different algorithm in the book called Simon's algorithm. This one deals with the problem of finding a hidden string. So the problem is as such: you have a function f of x that is equal to f of y only if x and y are the same. That's boring, right? F of x equals f of x. Or if you can add a string s to x so that y is equal to x c knotted with that string s. So let's give a concrete example. If n equals 3 and we select the secret string 110, then we would say all possible values of x are, for n equals 3, free bits, 0, 0, 0, 0, 0, 1, 1, 0, 1, and so on. So these are the 8 possible bit values that you can have. And then we calculate what that bit value C knotted with the secret string is. And you see these 8 equations. What this says is that here these two functions are the same, right? If you have 0 C knotted with 110 or 110 C knotted with 110, you can see that they are the same because they say on the left side, if I plug in f of 0, or here on the right side, f of 0, that's going to be the same as f of 110. And the difference between them is this guy here is just the 000 bit plus the secret 110. And you can do that for the other terms as well. So you find 4 equalities from this problem. And you can rewrite them again just to remember that F00 is going to be the output 110. Or F001, this guy here is going to be the same as zero, 1, 0. Is that a mistake? F of 0, 1, 1 should be the same as f of 1, 1. That's correct. And it's always 1, 1, 0. Yeah, that's correct. Okay, so we have these 4 functions here, 4 equalities. And now the question is, if I do not know the secret string s, how often do I have to ask the function f about a certain output before I can deduce what s is? So if you do not know the function f or the string s, how often do you need to call it to find the secret string? That's Simon's problem. So there's, of course, a brute force approach. You can just query the function f of x with different inputs until you find 2 pairs where f of x is equal to f of y. If you happen to find this, then you can set up your problem and say, well, I know that my 011 string C knotted with the secret string S0, S1, S2 is equal to 101. And I know that 011 C knotted with 011 is equal to the 0 string. So I can simply, on the left side, C knot that whole expression with 011. Then I, like here, let's do this real quick. Here, using this identity, I can just write 011 here, and I can do the same thing here. I can write 011 in front of this guy, and then this here is going to go away. So so this is going away, right? This is just 0, 0. It doesn't do anything. So I'm just ended up with S0, S1, S2. And then on the right side, I have now the 011 C knotted with the 101. And then now this whole thing is what? Well, I can just calculate it. 1 and 1 C knotted gives me a 0. 0, 1 gives me a 1. and 1, 0 gives me a 1. So I end up with finding the secret string right away. However, I needed to get lucky and find this guy. And how expensive is it to find it? In the worst case scenario again, you have to go through half of the possible options and then one extra. So that can take a long time if you have a bad searching strategy. So how about the quantum algorithm? Here the idea is that we use a smart circuit to randomly generate a string that has the property of its dot product with S being 0. Okay, so that's the basic idea here. We use a circuit, and we won't go into the details of how the circuit works, but what it does is it guarantees to produce a string of numbers that will have a dot product with S of being 0. And don't be surprised, but it uses again a bunch of Hadamard matrices raised to the power n. Okay, so for n equals 2, what comes out of it is this set of probability amplitudes and states. So the math is a little bit unwieldy, so we don't dive into all of the details. But the thing that we remember is anytime we query this function, we're going to get a string. We get a string whose dot product with S is equal to 0. And once we have it, then we can do something cool, and that is combining the quantum part with the classical part. So Simon's algorithm is a combination of quantum and classical algorithms. So let's talk about how this classical part works. And let's use the example of n equals 5. So we know that there's a string that has 5 unknowns in it, and we want to try to find these 5 bits. So how many options are there? 31. Okay. So in order to find this, we do a call. So I guess 31 is the number of trials it would take in a classical algorithm. So first we use our quantum algorithm and call it once, and that produces a string. Let's say the string 1011, 101010. This string here is 2 to the power 5 minus 1 is the number of strings, possible strings here, secret strings, that do not include the 000 string. That's what 31 is. So we're trying to find the true answer, and there are 31 options. Okay, so the first call gives us this random string. And now we try to use this. What do we do? Well, we know that the dot product of this string with S is equal to 0. So we can write out that 1 times S0 C naughted with 0 times S1 plus 1 times S2 and so on is equal to 0. This is just writing out the dot product. And if we do that, we see that all of the terms that have a 0 here, they're just going to vanish, right? They're just going to go. And then we only have left S0 C naughted with S2. So this guy here, C naughted with this guy is equal to 0. Does this help us? Well, it helps us to realize that S0 and S2 have to be the same, because if the C naught of two strings give us a 0, then both of those strings must be the same. Then we do a second call. This time we use 00100. We know again that the dot product has to be 0. So we write out the dot product, and we see here that S2, which corresponds to this bit here, by itself, right? This is the only term. We're going to get a 1 times S2 has to be equal to 0. So now we know that S2 is equal to 0. But because we know this guy here, we know that S0 is equal to S2. So we also know that S0 is 2. So after 2 calls, we already know 2 of the strings. Now we do a third call. This time we get 11110. Now we get so we know already S2 and S0, so we don't have to worry about them anymore. But we can write out the other states and see now from this expression, if we look carefully at the dot product, we see that we have 1 S1 left. and we have 1s3 left. And those two are equal to 0. So s1 is equal to s3. Great. And now we call a fourth times. By now, there is a chance that we would actually not get further because we either get the 0 string or we get the strings that calls 1, 2, and 3 have given us. But since there are 32, 31 options, maybe we are lucky and the fourth call gives us a new string s that we didn't have before. If we have this one and plug it in, we again get a dot product. We have here the S3 and S4 are the same. And since S1 is equals to S3, we know that S1, S3, and S4 are the same. Great. And do we know that they're 1? Why do we know that they're 1? Because we already know that S2 and S0 are 0, and the string 0000 is not allowed in a problem. And since we know that those three must be 1. So our answer is, this is the hidden string. How many calls did it take us? 1, 2, 3, 4. So it was a lot faster than going through half of the options. Great. So that's Simon's algorithm in a nutshell. So in general, if you want to build a quantum algorithm, what are the parts of the mixture that you need? First, you typically can't get away with just plugging zeros and ones in. You need to use this idea that you can put the problem into a superposition. And if you put the inputs into superposition, sometimes you can do smart tricks. The smart trick typically involves restructuring the problem through the transformation with the orthogonal matrix into a shape where you see a structure that was previously not visible. So the algorithms we've seen today, Deutsch-Josza, and Simon's, they were reverse engineered because those people were smart and they kind of saw what happens when you run things with Hadamard matrices and whatnot, and they tried to find the simplest possible algorithms. So while they demonstrate something cool, they effectively just started this field of quantum algorithms. And today there's being a lot published on this front. Of course, what we really care about is not someone coming up with a smart algorithm, but rather someone finding a hard problem and solving that hard problem with a smart algorithm. And that's something that can be done actually. And we're going to see that in the next lecture, which will also conclude our series already. So with that being said, thanks so much and hope you enjoyed this. Take care.